we have gamma t and gamma I. These scaling factors can be split into a dimensional part, this part or this part also, and the dimensionless part that are gamma t star and gamma I star. The analysis of the dimensional part can help to find a physical meaning, in fact, at these scaling factors. For instance, for gamma I, this quantity can be considered as the quantity of water we need to fill the profile over the depth Hg from a very dry initial state to the saturated state. In fact, for green and amp soil, it will correspond exactly to the quantity of water above the groundwater, between soil surface and the groundwater. So this will be considered as a characteristic infiltration, in fact, and it has the unit of a length. For gamma t, we can see that it corresponds to the previous quantity, except that we divide by Ks, which is the infiltration rate we have when we reach steady state and when the soil is profiled. So gamma t can be seen as the time needed to fill this quantity of water with an infiltration rate equal to Ks. The dimensionless part can be expressed as a function of the initial and final saturation degrees and the shape parameter of the hydraulic conductivity function. In our study, we considered, or we made all the calculation considering Van Genurten mu-lm model for water retention function plus mu-lm capillary hydraulic conductivity model for the unsaturated hydraulic conductivity. And we will try to quantify these variables. So I begin with the dimensional part of scaling factors. Table 1 lists the values that we may obtain for the 12 soils that were defined by Kersel and Parrish in 1988. So I just listed here the values of the hydraulic parameters and the numerical values in minutes and millimeters of the scaling factor for time and infiltration. And we can see that we have a gradient of value between coarse soils with mostly small values to fine soil with much larger values. This can be explained by the fact that in fine soil you will have a lot of capillarity, and then you will increase the quantity of water there that you can store in the profile. And in addition, as fine soil has very small hydraulic conductivity, you will increase a lot the time needed to feed or to supply this quantity of water. So in fact, the values of the scaling factors may help to separate the types of soil between coarse soils and fine soils. For the dimensionless part of the scaling factors, I investigated the influence of the initial saturation degree before investigating the effect of the final saturation degree. So for the initial saturation degree, this is figure 2, and we get here this dimensionless scaling factors for infiltration and time as a function of the initial saturation degree and for several values of n. So we have here n equal 1.1, 1.25 up to 3. And we can see that, of course, this quantity depends on both the initial saturation degree and the shape parameter n. But there is a mean to synthesize the information. I mean, if you consider these quantities for each curve and you divide by the maximum that correspond to 0 initial saturation degree, then you will get this simplification with all the curve will align on a straight line that correspond to y equal 1 minus x. And this is all more true that the initial saturation degrees is lower than a quarter of the final saturation degree. So this law is important because or this finding is important because it helps a lot the computation of the dimensionless scaling factors. Indeed, if you know the initial saturation degree and you know that it's not that large, you can apply this approximation. Then you can approximate your scaling factor with just a linear function there that you multiply by the scaling factors that correspond to a very dry initial state and the final saturation degree SE1. So this equation was proposed by Averkamp for only the case of the final saturated conditions, but in our case we demonstrate it using numerical computations for all cases and any value of final saturation degree. So we can see this result as a generalization of the relation proposed by Averkamp et al. And also it simplifies. When we have simplified the computation, we just need to compute the scaling factors between 0 and the final saturation degree. So you have here this computation for time and infiltration, and also you have a zoom, in fact, at the end when the saturation degree, at the final saturation degree, tend towards 1. You may be surprised by the huge values that we may obtain for these scaling factors, but in fact that's normal. These are representative of the contribution of the capillarity, and of course when you decrease both the initial and final saturation degrees, you boost the effect of gravity. The effect of capillarity, and then you will boost the values of the scaling factors.